Sometimes the absolute smartest automated system in the world just needs a human to step in and say, nope, not right now. Welcome back. Today, we're tackling one of the most fascinating aspects of modern power generation, manual authority. We've spent a lot of time in this explainer looking at how the Caterpillar C175 engine protects itself, but today, we're flipping the script. We are looking at exactly how we override those protections by exploring the emergency override panel. So let's dive right in with a fundamental question. What actually happens when you need to bypass a C175 engine's self-preservation logic? Now, we all know the electronic control module, the ECM, is an incredibly smart piece of tech. It's constantly monitoring temperatures, pressures, and speeds to keep that engine safe. But as you'll see, there are very specific times when all that brilliant automated logic has to take a backseat to human judgment. And this right here perfectly illustrates where that human authority lives. This is the Caterpillar override switch panel, which is housed securely right inside the local control box. It represents the ultimate manual authority. It's your way to bypass automated logic safely and deliberately. Because, look, the automated logic is right 99% of the time, right? But for emergency troubleshooting or highly specific maintenance scenarios, a technician really needs the ability to directly intervene. Okay, here's our quick roadmap for today's explainer. We'll hit the authority to bypass, break down the 5 override switches, dive deep into the engine protection override, weigh risk versus reward, and wrap up with external controls and e-stops. Let's get right into Section 1, the authority to bypass. You might be wondering, why would we ever want to turn off the safety systems of a multi-million-dollar piece of equipment? Well, there's this constant philosophical tension between the engine's built-in default programming and a technician's need for manual control. The ECM is hardwired for hardware preservation, but what if you just need to test a starter circuit? Or picture this, what if the engine is powering a hospital during a massive power failure and some minor sensor fault is threatening to shut the whole system down? In those high-stakes moments, human judgment simply has to override the machine's default parameters. Moving right along to Section 2, the 5 override switches. Let's look at the exact tools a technician has at their disposal here. The sheer specificity of these controls is honestly pretty cool. There are exactly 5 switches on this panel. You've got crank OVRD, which lets you manually engage the starter motors. ENG-PRTN OVRD, or Engine Protection Override. We'll talk a lot more about that one in a second. Then there's MNL-PR Lub, which manually kicks on the pre-lube oil pump, super essential after an oil change. Low idle cell forces the engine to hold a low idle for warm-up testing. And finally, Rapid Start-Stop, which just toggles your high-speed start and stop sequences. So the really crucial takeaway here is how these switches totally alter the engine's behavior. In its automated default state, the engine is calling the shots. It waits for a full start sequence, it runs its own automated prelube, and it manages its own idle timing. But the second you flip one of these override switches, the technician takes the reins. You want a direct starter test without actually firing the engine? You got it. Need to force a manual oil prime to check your pressure? Done. It's all about handing complete, granular command over the machine subsystems right back to the human. Now for the heavy hitter. Section 3, Engine Protection Override Explained. The nuclear option. Out of all those switches we just looked at, there is one that absolutely stands alone. ENG-PRTN OVRD. This literally means protection off, emergency use only. Guys, this is the most critical and, frankly, the most dangerous switch in the entire control box. I really can't emphasize this enough. This is the nuclear option. When you flip this switch, you are completely disabling the ECM's protective derate and shutdown logic. All those safety nets, the low oil pressure shutdowns, the extreme temperature derates, poof, they're gone. The engine goes completely blind to its own self-destruction parameters. And that brings us to a very heavy concept in the power generation world known as run to destruction. Basically, this means operating an engine way past its protective shutdown limits during a severe emergency. You are actively accepting internal mechanical failure. You are literally willing to melt the engine from the inside out, just to maintain critical power. You only make this call when the consequence of the engine stopping is infinitely worse than the consequence of losing the hardware. Which leads us directly into Section 4, risk versus reward. Operating with this level of manual authority takes a huge amount of situational awareness. The best way to think about the engine protection override is to compare it to the fire suppression handle in an airplane cockpit. You know, the one covered by a little piece of breakable glass. You never ever touch it during routine operation. You only pull it in a genuine life or death emergency where doing nothing is catastrophic. Using an override just to bypass an annoying alarm, that is exactly the kind of misuse these safety covers are meant to prevent. So let's test your logic with a real-world scenario. Imagine you're running a routine load test on a generator. Suddenly, a minor temperature derate kicks in, and it starts slowing the engine down. It's mildly annoying, and it means you probably won't finish your testing schedule for the day. Should you go ahead and use the engine protection override to bypass that derate just to get the job done?
The answer is a definitive absolutely not. No. You never use overrides for nuisance alarms or scheduling convenience. If you treat this switch like a convenient shortcut, you're inviting catastrophic mechanical risk for zero emergency benefit. It's a deliberate trade-off, right? You never trade a $1 million engine just to save 30 minutes on a Tuesday afternoon. Okay, let's wrap things up with Section 5, external controls and e-stops.
Now that we grasp the gravity of local overrides, let's zoom out a bit. How does the engine actually talk to the rest of the facility? When you're paralleling multiple generators together onto a shared electrical bus, the engine's ECM has to take orders from a higher-level governor. Very often, that's a Woodward 2301E. The signal path is pretty brilliant. The Woodward sends out a simple 0 to 200 milliamp analog speed bias signal. It's basically whispering, hey, give me a little more or give me a little less. The CAT ECM takes that current, translates it into its own digital language, a pulse width modulation or PWM signal, and then uses that to physically adjust the fuel rack. It's a seamless translation from analog current right to digital mechanical control.
And because of that external communication, the engine can operate in two totally distinct ways. First, you have droop mode. This is all about proportional load sharing. When multiple generators are tied together, droop lets the Woodward governor slightly dial back engine speed as the load increases, making sure all the engines share the electrical burden evenly. Contrast that with isochronous mode. Isochronous is constant, locked speed operation regardless of the load, which is typically what you use when a single generator is running the whole show by itself. Finally, we have to talk about the ultimate external control, the emergency stop, or e-stop. Now, unlike our manual overrides that force the engine to keep running, an e-stop is designed to kill it instantly. These are hardwired inputs. The second one gets hit, the ECM instantly kills fuel injection via the basic engine logic. But here's the crucial takeaway. An active e-stop causes a latched shutdown. You can't just pop the button back out and hit start. Nope, it demands a hard reset. You have to completely cycle the key switch, power to the ECM, to clear that latch before the engine will ever crank again. While we have covered a massive amount of ground today, from the delicate translation of analog signals all the way to the heavy reality of run to destruction, I want to leave you with this final, somewhat provocative thought. We put incredible technology into keeping these engines safe. But if the grid fails and lives are on the line, are you truly prepared to flip that switch, take manual authority, and make the call to sacrifice an engine to save a facility? It's a massive responsibility, but understanding these systems inside and out ensures that if that day ever comes, you are making the right choice. Thanks for hanging out with me on this explainer. Keep learning, and I'll catch you next time.